The Big Bang Theory is our best explanation for how the universe began. It describes the expansion of space itself, an expansion that continues to this day. Before the Big Bang, there was no space, no time, and no matter as we know it. Everything we observe today was compressed into an infinitesimally small point called a singularity. This singularity wasn't located somewhere within a pre-existing space. It was the seed of space and time itself. In a fraction of a second, the universe underwent a rapid expansion, growing exponentially in size. This period, known as cosmic inflation, is crucial to understanding the universe's uniformity and the distribution of matter and energy. The Big Bang Theory is supported by a wealth of observational evidence, including the cosmic microwave background radiation and the redshift of distant galaxies. The Big Bang model provides a framework for understanding the universe's evolution and our place within it. Imagine a universe smaller than an atom. This is where our story begins, in the first fraction of a second after the Big Bang. At this stage, the universe was an unimaginably hot and dense soup of energy. As the universe expanded, it cooled rapidly, allowing the fundamental forces to separate from one another, a process known as symmetry breaking. Within the first second, the universe had grown from an infinitesimally small point to the size of our solar system. It was still an incredibly extreme environment, filled with high-energy particles and radiation. But as the universe continued to cool, conditions became favorable for the formation of the first particles of matter. This early universe, though chaotic and extreme, was governed by the laws of physics as we understand them. By studying the remnants of this early period, such as the cosmic microwave background radiation, cosmologists can piece together the story of the universe's first moments. The Big Bang model, while successful in explaining many aspects of the universe, faced a few puzzles. One such puzzle was the horizon problem. The universe, even at vast distances, appears remarkably uniform in temperature. The answer lies in a period of exponential expansion in the universe's very first moments, known as cosmic inflation. During inflation, the universe expanded at a rate faster than the speed of light. This rapid expansion had profound consequences, flinging regions apart and carrying their uniform temperature with them. Inflation also stretched out any initial quantum fluctuations, leading to the large-scale structures we observe today, like galaxies and galaxy clusters. While we don't have direct observational evidence of inflation, the predictions it makes about the universe's large-scale structure align remarkably well with observations. As the universe continued to expand and cool after inflation, a remarkable transformation took place. Energy began to convert into matter. This wasn't just any matter. It was the fundamental building blocks of atoms, the particles we know as quarks, electrons, and their antimatter counterparts. In the early universe, the energy density was so high that it allowed for the spontaneous creation of particle-antiparticle pairs from pure energy. However, a slight asymmetry between matter and antimatter led to a crucial outcome. As matter and antimatter particles collided, they annihilated each other, converting back into energy. But that slight excess of matter meant that some particles survived this annihilation process. These survivors, the quarks and electrons, would eventually form the protons, neutrons, and electrons that make up all the atoms in the universe today. By the time the universe was a few minutes old, it had cooled enough for another crucial process to begin nucleosynthesis. This was the cosmic cookbook moment, where the simplest atomic nuclei, those of hydrogen and helium, were forged from the protons and neutrons created earlier. In the intense heat and pressure of the early universe, protons and neutrons collided and fused together. The simplest nucleus, hydrogen, consists of just a single proton. Helium nuclei, with 2 protons and 2 neutrons, were also formed in abundance during this period. Nucleosynthesis is a delicate dance of forces and conditions. The Big Bang model predicts the relative abundances of hydrogen and helium that should exist in the universe today, and these predictions match remarkably well with observations. This agreement between theory and observation provides strong support for the Big Bang model and our understanding of nucleosynthesis. After the fury of nucleosynthesis, the universe entered a period known as the Dark Ages. This era, which lasted for hundreds of millions of years, was characterized by darkness because stars, the universe's cosmic lighthouses, had yet to form. The universe was filled with a mostly uniform soup of hydrogen and helium gas. Gravity was slowly at work, pulling matter together into denser regions. Over vast stretches of time, these density fluctuations grew, eventually becoming large and dense enough to collapse under their own gravity. As these clouds of gas collapsed, they heated up, and the pressure at their cores increased dramatically. Finally, the temperature and pressure at the core of these collapsing clouds reached a critical threshold, igniting nuclear fusion. The first stars were born, likely very different from the stars we see today. Their intense radiation ionized the surrounding neutral hydrogen gas, effectively ending the Dark Ages and ushering in a new era in the universe's evolution. One of the most compelling pieces of evidence supporting the Big Bang theory is the existence of the cosmic microwave background radiation, or CMB. This faint afterglow of the Big Bang permeates the entire universe. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms. This event, known as recombination, had a profound effect. Before recombination, the universe was opaque to light, as photons were constantly scattered by free electrons. After recombination, the universe became transparent. The photons that were released at this time have been traveling through the universe ever since, gradually losing energy as the universe expands. Today, these photons reach us as faint microwave radiation, their wavelengths stretched by the universe's expansion. The CMB provides a snapshot of the universe as it was just 380,000 years after the Big Bang. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery that revolutionized our understanding of the universe. By observing distant galaxies, Hubble noticed that the light from these galaxies was shifted towards longer wavelengths, a phenomenon known as redshift. Redshift is analogous to the Doppler effect we experience with sound waves. Just as the pitch of a siren drops as an ambulance moves away from us, the wavelength of light from a galaxy is stretched or redshifted as it moves away from us. Hubble's observations revealed something even more profound. The farther away a galaxy is, the faster it appears to be moving away from us. This relationship, now known as Hubble's law, implies that the universe is expanding, with galaxies moving apart from one another like dots on an inflating balloon. The discovery of the expanding universe provided crucial evidence for the Big Bang theory. The redshift of distant galaxies is a direct consequence of this expansion. The fate of the universe is a question that has intrigued cosmologists for decades. Will the universe's expansion continue forever? Or will it eventually slow down, stop, and reverse, leading to a big crunch? The answer to this question depends on the balance between the outward push of expansion and the inward pull of gravity. If the universe contains enough matter and energy, gravity could eventually halt the expansion and cause a collapse. However, if the universe's density is below a critical threshold, expansion will continue indefinitely. Current observations suggest that the universe's expansion is not only continuing, but also accelerating. If dark energy continues to dominate the universe's expansion, the universe will likely expand forever, becoming increasingly cold and diffuse over time. The Big Bang theory has profoundly impacted our understanding of the universe and our place within it. It has shifted our perspective from a static, unchanging cosmos to a dynamic, evolving universe with a beginning and potentially an end. The Big Bang model tells us that we are all made of stardust, forged in the hearts of stars that lived and died billions of years ago. The atoms in our bodies, the air we breathe, and the earth beneath our feet were all once part of a hot, dense sea of particles and radiation in the early universe. The Big Bang theory also raises profound questions about the nature of the universe and our existence within it. What happened before the Big Bang? What is the universe expanding into? Are there other universes out there? While we may never have all the answers, the Big Bang theory provides a framework for understanding our place in the grand scheme of things. It inspires us to continue exploring the cosmos, seeking answers to fundamental questions about the universe's origin, evolution, and ultimate fate. The journey of cosmic discovery that began with the Big Bang is far from over.